So, good afternoon. I just realized that the problem 3 I haven't talked about it either in class, and then I forgot completely. Very interesting question. Before we go and do that, however, let me go again a little bit through what we mean by constraint programming. Has everybody watched the recording of Friday's lesson? Okay, good. So what we learn through constraint programming is the following, that unlike mainstream programming, where you have computation requires the computation of a value essentially that is stored somewhere, right? So that's what we do. Compute an expression, store the value somewhere, and essentially every variable has a value, right? Even though it might be random. You haven't initialized the variable, right? So you don't know what the value is. It's random, but still is. If you try to print it out, you get a printout of a value. In Prolog, if you remember, variables can be unbound. Start as unbound, then we bind them, and then they take a value, and that value never changes. And the upside of that is that we can specify relationships between variables that, even though we don't know that those variables would have a value, right? I can say x is not equal to y, and I don't care right now whether x and y have values. The system will look at them and say, well, if they have values, I can test and decide whether they're true or false. But if they're not, they don't have value, if they're unbound, I can delay the constraint and reprise it, come back to it whenever I have more information about x and y. Okay? So that's essentially what's happening. I can say something about a variable without knowing its value. So for instance, we can say x equals y plus 1, and now it looks very ugly. I don't know. I said something probably. Did I said something wrong? It should print nicely y plus 1 equals x, but maybe I put in a top level print. What else did I?
Maybe the portray or quote might be set to false.
Yeah, I think I need to set all of them. So let's do this again and say quoted. Yay. All right. So, so we don't know the value of x, we don't know the value of y. We say that x is equal to y plus 1. System accepts it and delays it. And what we get back is whenever, if we haven't computed, if we haven't gotten to the point of computing a value for x and y, the system is very happy to just report whatever it has. So we may go further and add more information. So we might, for instance, say that x is 3 minus y, for instance, right? And now you're going to say, well, it's a system of 2 linear equations, right? With 2 unknowns. So we have enough information to decide what the value is, right? So x should be 3, so x should be 2, and y should be 1, right? But the system is not smart enough. It's not smart enough because the procedure for deriving values, deriving information about its delayed relationships is not necessarily very strong. And it actually can be chosen by us. We can choose between several procedures. We have chosen for the time being to use the library of finite domains, and the library of finite domains is not as strong. I can switch, we'll see in a minute, to a library called CLP on real numbers, CLPR, which can solve this without any problem. And actually, let's see if we can do this right now. And hopefully they won't interfere with each other. So this library is a bit different, has a slightly different syntax. We have to put everything in curly braces, but then we can use the equal sign that we are used to from mathematics, right? But the equal sign inside curly braces has a different meaning as opposed to the one that is used outside curly braces. So now this is solved, right? But it only solves linear equations, and it only solves them on reals. And you might say, well, you know, probably reals is more difficult than integers. Not true. Integers is much more difficult than reals. So often enough, we want actually integer solutions, and we don't have the luxury of having linear equations all the time. So going back to this one, which hopefully, let's try again and see whether there's any interference. No, hopefully. What do we do here? How do we solve this one? If all we have is finite domains, how do we solve this one? How do we get more information? Well, the idea is, as you already know, because we discussed this before, to generate combinations of tries, of attempts, right? We start with making some guesses about x and y. So, you know, looking at it, we can pretty safely assume that the solutions for both x and y are going to reside in the -10 to 10 interval, right? So let's just say that. So both x and y, right? But I'm gonna use separate domains because we're gonna see soon why is that. -10 to 10, and y might reside between -10 to 10 as well. And now, if I give this to the system, right? So the system will process this from left to right. It will process the first constraint. These relationships, we call them constraint. We'll process the first constraint, then the second constraint, right? In both cases, it says I don't have enough information, so I'm just going to put it there. Now, when we have the added information of x being between -10 and 10, the system will try to propagate the new constraint. Will try to use the new information against the information it already has. So when it says, well, this is -10, then it will immediately, sorry, let's start with this one. When it sees that x is 10, it will immediately derive that y cannot be larger than 9. So even before it sees this, it will set an upper bound for y at 9. All right, so you see y is not 10. And then when it sees that x is 10 also here, it will see immediately that y cannot be lower than -7. So the bound that we have set on x is immediately propagated and entails a bound on y. So the system doesn't stay exclusively with the bounds that we are trying to specify. When x being -10, let's see what that entails. So when x is -10, when x is -10 here, that doesn't help us in any way. All right, so now the interesting thing is the following. We have new bounds for y. And what will the system do? We'll go again and try to propagate the new bounds on y through the entire set of constraints. And the -7 here, right, will entail that x cannot be lower than -6. So you see a bound of -6 here. Okay? So essentially, whenever we work on finite domains, what happens is that the system will retain bounds, limits, for every variable. And whenever it acquires more information, it will try to shrink these limits. We start with a large domain, and every iteration, every processing that is done through the constraints is trying to shrink the domains. If all the domains are brought to singletons, then we have found a solution. If we have come to a case where at least one of the domains is empty, we have reached failure. Otherwise, we don't have enough information about the solution, so we're just going to print whatever it is. So hopefully, we are trying to reach the place where every domain is a singleton. Right? That's what we're trying to do. And it's not always possible, but we can somehow force it all the time. What next? What can we do next? Well, we say all the information we have now is that x is between minus 6 and 10, and y is between minus 7 and 9. So I am going to force a search. I'm going to say to create alternatives. So x being between minus 6 and 10 can be perfectly equivalently written as n and x being equal to minus 6 or x in minus 5 to 10, right? So I'm going to say it's the same thing. What difference does it make? Well, it makes a difference. Now it creates two separate search processes. One where x is equal to minus 6, and one where the domain has shrunk. So if the domain cannot shrink by propagation, we try to divide and conquer, right? We try to create several problems, each of them with smaller domains, and every time the domain shrinks, that shrinkage of one domain may entail shrinkage of other domains. And this is indeed what happens if I were typing correctly. Something is wrong. What? Operator expected the minus. Very good. So you see, again, this one could not have succeeded, because if it had succeeded, we would have gotten one solution. One value of x, a single value of x, will entail at most one value of y. So we cannot be getting a domain back from an attempt to give x a singleton value, right? So it means that this one has failed, right? And this one actually hasn't succeeded. We doesn't have enough information to derive a full solution, but this is what the system is left with, so this is what it prints. However, notice how the domains are shrinking. So we are saying that the lower bound here is minus 5, but we were happy with the 10 here. However, the system has inferred a 9. Propagation has shrunk the domain further. And for y, previously we had y between minus 7 and 9. Now y is minus 6 to 8. Okay? So now I want you to think of the following thing. We are creating a search tree. We are creating alternatives. So I'm giving an alternative here. Now I'm going to go here, right, and create a new alternative. I'm going to create more alternatives for x, right? And more alternatives and more alternatives. And since the initial domain was for x between minus 10 and 10, so that's 21 values, and for y, minus 10 and 20, that's another 21 values, right? The potential search space could have been 21 squared. I'm not very sure how much that is, but it's in excess of 400, so it's a relatively large number. So the question is now, will we have to go through all the 400 attempts? And you can sort of see already that the answer is going to be no. Why? Because every time when I propose a shrinkage of the domain, the system responds with further shrinkage. So every choice point is not by just one pair of the search space. It eliminates several pairs of the search space, right? So I'm probably going to finish quite quickly. I'm not going to create 400 and something separate tests. Is this clear? So now I have here minus 5 and 9. So we're happy to request a split again. X is minus 5, or x is in minus 4 to, now we have 9, right? So let's try this one. So again, we are requesting, so the first one could not have succeeded because the response to this would not be an interval, right? So it must be that this has failed, this have led to failure, and you can very quickly verify, right, that if x is minus 5, I cannot satisfy both these equations simultaneously, right? So it must be that this attempt has failed, and I'm left with this one. But the shrinkage that I have proposed from minus 5 to minus 4 has entailed further shrinkage achieved by the system through propagation of the new bounds through the set of constraints. So now x is between minus 4 and 8, and y is between minus 5 and 7. So we shrink further and further. So let's shrink some more. Right, so now we try x being equal to minus 4 and or x in minus 3 and 8. Right? So again, more shrinkage, and we're going to continue the process. And the interesting thing is, how many of them do we need? Minus 3 or x in minus 2 and what's now there, 7. Right? So more shrinkage. So you see, every time I shrink the left-hand side, system derives that the right-hand side should of the interval should shrink as well. X is minus 2 here, and x in minus 1 and 6. All right. Further, we have x equals minus 1 or x in 0 and 5. Right, so again, more shrinkage. X 0, x 1 in 1 to 4. All right, we're getting close. So next one, we're going to see actually the solution, and that's going to reveal something interesting as well. Right? So now we get the final solution. And what happens is interesting. This one has failed, right? As it happened before. And the second one, we have proposed an interval. Even though it's an interval, the system was able to derive the unique solution, right? So sometimes the way the constraints are propagated leads to a unique solution, even though the original domains are non-singletons. So here what's happening is that x being equal to 3, right, x being equals to 3, it's actually more related to the fact that the previous domain, so x being equal to 3 leads to a domain in y of 0 to 2. X being equal to 2 here, x being equal to 2, so the maximum is 2, means that x cannot be greater than 2 here, right? X cannot be equal to 3, so that eliminates the solution, and we are forced into a unique solution. Now, so how many choice points did it take? It took 1, 2, 3, 4, 5, 6, 7, 8, instead of 400 and something, right? Which would have been the worst case if we had tried all of them, right? So propagation makes constraint solving very efficient. You're thinking in general that, yeah, our genetic combinations, it must be very inefficient. Not true. A lot of the combinations can be eliminated up front because of this constraint propagation. Obviously, we don't have to do this like that. In our programming, there is a procedure that does this splitting for us. What is it called? We've seen it before. Right, label. So I can label xy, and I get the solution. I don't have to. It will do exactly what we saw. All the sequence of 8 splittings, it will do it for us. And actually, on all the sequence of 8 splittings, you have seen that we have never touched y. So you may think that we want to generate combinations for x and y, but since we haven't touched y and still managed to reach a solution, we can just generate combinations for x. That's enough, right? X will give us enough refinement of the domains to get to the unique solution. Is this clear? So the important thing that you need to understand here is from a language perspective, right, how two paradigms have been married together. So there's the paradigm of constraint solving, and there's the paradigm of logic programming. Both of them have something in common. Have the need. So the constraint programming needs variables that are not assigned. Needs variables that remain unbound through the process of computation, right? Logic programming provides such variables. So it was a natural marriage between the two. So constraint logic programming represents an embedding of a constraint language into a logic programming language, right? So it pertains to embedding a language, embedded languages. That's what's happening here. And you can see that the language is very powerful. We have already solved a few puzzles, and if you think of how would you solve those puzzles without this kind of tool, if you wanted to do it in C or Java or Python, right, you would get much more complicated programs. You would spend much more time, possibly a lot more time debugging as well, not just writing the program. All right, so questions so far? This is the process. It can be done. It's not necessarily efficient, but it's much more efficient than you would have expected, right? That's the important perspective here. And it's elegant, it's natural, it's very powerful. Do you have questions so far? Should we move on to try and solve the puzzles that we have for today? So the first puzzle is puzzle number 3. All right, 10 cells numbered 0 to 9. Inscribe a 10-digit number such that each cell, say I, indicates the total number of occurrences of digit I in the number. Model this problem with constraints and write an Eclipse query that solves it. Let me give you the solution first, so you understand exactly what we're talking about. Maybe that's takes a while. All right, and let's understand exactly what we mean. So on this position corresponds is rank 0 in the list, right? We have a 6, means that we have 6 zeros in the list, right? This is rank 1. We have 2 1s. This is rank 1. We have 2 1s in the list. This is rank 2. We have 1 2. One occurrence of the number 2. This is rank 3. We have 0 3s. This is rank 4. We have 0 4s. This is rank 5, 0 5s. This is rank 6, 1 6. Rank 7, 0 7s. Rank 8, 0 8s. Rank 9, 0 9s. Is this clear? That this is the solution, right? This is what the problem is asking. So let's see how we solve this. Let's sort out the problem of occurrences. So how do we count the occurrences? All right, and people have tried to write their own predicate. Always we have to try to use as much of the predefined stuff as possible. So let's say I have a list L, which is exactly this one. Why not this one? So 6 2 1 0 0 0 1 0 0 0. And we want to find out the number of occurrences of the value, let's say, 2. Or maybe 0, because let's make it interesting from the very beginning. So, what will tell me whether 0 occurs in L? V occurs in L. Obviously member, right? I'm going to check member VL. So, if I do member VL, right, I'm going to find out, I'm going to succeed a number of times equal to the number of occurrences, right? How do I put all these solutions into one answer? So I don't want 6 separate answers. I want all this stuff aggregated into one answer. Anybody knows? It's actually the same solution, but I want, so let's try a different thing, right? So let's say I have x equals 1 or x equals 2 or x equals 3, right? So this succeeds 3 times. How do I see all the solutions in one answer? Do you remember find all? So I want a, let's say x. This is my goal, and I want the answer collected into a list, let's say L. Right? I can put any goal here that succeeds multiple times, and I can take something like this and convert it into something like this, right? So if I do the same thing here, I say find all, and now I can, in principle, I can put anything here. I can put the anonymous variable. I'm not interested in the answer per se. I want the number of occurrences. So since I'm going to get a list, what is going to tell me the number of occurrences? The length of the list, right? So I'm going to collect this answers into some list T, and I'm going to say length T, and this is going to be my number n, right? So there are 6 zeros, and if I want to find the number of ones, I'm going to have 2 ones, right? And if I want the number of sixes, it's going to be 1, and if I want the number of sevens, it's going to be 0, right? So the number of occurrences can be found out by a simple expression, right? The expression is this. What's to the left of this is the input to the expression, and we're going to take this expression that I have just highlighted and use it in our solution, our predicate, to compute the number of occurrences. Is this clear? So I'm going now to the solution. So the solution is a list L, right, which has 10 elements. So you see, I'm not saying what L is, but I'm saying that L is a list of 10 elements. So L will be created as a list of anonymous variables. If I say length L10, what I'm getting is a list of variables, and these variables can be bound later to something, and it's going to be bound to these numbers later, right? Now there's another question that I have for you. Is there anything interesting about the list L? Is there some property that of the cuff you can say? How about the sum of the elements? Pardon? It's always 10. If you look carefully at the description of the solution, you will easily infer that the list must have the sum equals to 10. Okay? So that's going to help us later. Keep it in mind. All right? So we start with a list of placeholders that has 10 elements. Each element of the list has to be confined to be between 0 and 9. So the interesting thing about SWI prolog is that it can specify not just a variable, but a list of variables, right? So previously you have seen x in minus 10 to 10. Now we can have a list xy, right? And and each of the variable in the list xy being confined in a domain, but the predicate for that is in ins, right? Like the plural. In is singular, ins is plural, though it doesn't make sense because in is a preposition and it doesn't have a plural. But nevertheless, that's what they're trying to say, that if a single element is in something, a list of elements should be ins some domain. Then this is redundant, but will speed up the search. So we'll see what happens if we remove it, right? It will help us generate more combinations. We have a bit of trouble. It would be nice if we could put the label after iterate, and if iterate was completely constraint based. However, this iterate predicate is based on find all, member, and length, which are part of the library, and they're not constraint based. They don't define constraints, they specify computation, right? So because of that, we cannot create relationships between variables using these predicates and then try to assign the variables. So we have to do the labeling first. All right? If I'm going to remove the sum, right, you see that the sum there is a predicate that computes the sum of elements of a list. But I'm not using that one because I want to create the sum as a constraint, as a delayed thing. So I'm going through the list of unbound variables and I'm constraining them without giving them values. I'm constraining them to sum up to 10. Okay? That will limit the number of combinations that I can generate. And then I generate combinations of lists whose elements sum up to 10. It's much less than the number of lists with all possible combinations of elements. I can only use iterate after that. I can only call iterate when the list of elements, the elements have values, because I'm going to use on the member and length. So now I'm going to do iterate, which is going to do what? It was going to impose the constraint that we have just seen, but previously we have seen this constraint for individual elements. So we have tried the 7, we can try the 6. I have to iterate through all the values from 0 to 9. Or from 9 to 0. Okay? And actually, I'm going to iterate from 9 to I'm iterating from 0 to 9, but I'm going to iterate from 9 to 0. I'm going to iterate from 0 to 9 this time because that will speed up the process. Let's use a plot. So what do we do? Right, so when we were here, we were careful that v be a specific value between 0 and 10, right? But then, here, how do we create the relationship between the rank and the value? Well, we have this and 0 that does that. So if L is a list, give me n as a rank between 0 and 9, and v will be the value that is sitting on the element with that rank in the list, right? So if my list is this one, and 0 of 0 and L is going to be V, and V is going to be 6, right? And if I'm going to change this to 1, I'm going to get 2, and so on and so forth, right? So I'm selecting the element of rank n, that's V, and V has to be the number of occurrences of n in my list. So I'm going to use the two predicates that we have just discussed, right? So I'm counting the number of occurrences of n in the list. I'm going to obtain a list T whose length must be V. Okay? So this is one iteration. And then I have to do this for all ranks. So I'm going to move on to the next rank, and I'm going to iterate again, and I'm going to stop at 10. Okay? So this is the program. Now, the sum, as I was saying here, is redundant. So Let's run it. This time we're going to go even faster because I have changed the order. Actually, not a lot faster. But we get a solution. All right? And let's see what happens if I don't use the sum. So now we see how redundancy can be useful. So it's going to take much, much longer. Okay, so I'm going to do some printing. When I do some printing, I'm not going to be able to stop it. So let's write here, write line L, and see what's trying to do. So I'm going to have to restart after that. All right, so you see the combinations being generated in lexicographic order, very, very slowly, right? I know what will speed it up. Reversing the list will speed it up. Let's see if we're lucky enough to be able to stop it. No such luck. Oh, okay. Luck. First time it happens. But not. Okay. So now let's go and put back the sum and see what is being printed then. So they have to add up to 10. You see the process is much faster. You see the 1 propagating towards the left much faster. So now since the first element has to be a 6, you see they're propagating from left to right. How can I speed this up? Actually, already said. If I'm going to reverse the list, I'm going to reach that 6 much faster, right? 6 is a pretty big number, so it restricts the remaining 9 variables to add up only to 4, right? So when that restriction is enforced, then there's a lot less choice. So you see, this is heuristic and constraint solving. Well, of course, it's much slower when it prints. So we have to get a 6 in the first column. Well, you believe that it will get there, right? We've seen it get there already. Well, okay. So now let's reverse the list. Before the label or after the label? I think after the label. Okay, much faster. Reversing the list helps a lot. Now, the thing is that it won't help with the full termination of the program, right? So if we want to check that the program is has a unique solution, then we will have to go through the entire list, to the entire set of solutions. But otherwise, if we find the first solution, then it's fast. Then it's fine. Is this clear? Okay, so this is the program, right? Notice how redundancy can be useful, right? So the sum we would find the solution without having the sum there, right? But we are limiting the number of combinations because of that. Okay, we move on to the next question. Exercise. So the next one is very interesting. It's a famous puzzle. I think it's an adaptation after Carol Lewis. So and it's a very typical one, right? So if I have 5 properties, nationality, we have 5 houses, right? Which have an owner, the owner has a pet, the house has a color, there's a drink, the owner drinks a certain drink, and there's a car that is driven by the owner, right? So we can think of the houses as having numbers 1 to 5, and we're curious, right, for each house, who lives there, what pet that person has, what color the house is. So it's 5 types of properties, 5 values, possible values for each of the properties, in total 25 properties. And we want to find out what they are based on these constraints. I'm not going to read the constraints to you right now because they're not so relevant. What the constraints are is not so relevant. How we encode the constraints, that's very relevant, and that's that when we do that when we see the program. So I'm going to move to a different prologue because I already have the solutions, but they're written in Eclipse, and the syntax is a bit different. It's not very, very different, but a bit different, and I don't want to go through the trouble of rewriting everything. So we're not going to worry with. So these are solutions that I used to teach in a different module. We are going to stay minimal. So we have 25 variables, right, in 5 groups, 5 properties. Each property defines a group of 5 variables with 5 possible values, of course, each of them. We're going to, in order to perform a very nice encoding, to have a very straightforward encoding, we need to set up things a little bit. And actually, this looks like very complicated, but it's just a way of making the printout more readable. So we're going to print out a list of lists, right? Where we're going to have something like English. This is an atom, right? So it will remain in this form. And this is a variable which will take a value in the end, which will be between 1 and 5. So you're going to see something like English equals 3, which means that the English person lives in the 3rd house, right? And so on and so forth. Ukrainian equals to whatever 4 means Ukrainian lives in the 4th house. Milk equals 3 means that milk is drunk in the 3rd house, and so on and so forth, right? So we're defining the variables, and their labels. The atoms are sort of labels that will appear in front of the variables when they are printed. And then we're going to print this list as soon as all the variables have gotten their values, and that will make the printout more palatable. So this is not much, right? The setup actually starts here. We need to group all the variables by the property to which they belong, right? So we have people, we have colors, we have drinks, we have pet, we have cars. Each group contains 5 variables. And all these 25 variables, when they are put together, and we're going to do that here, right? We do this, we call this predicate append all. which flattens this list. Notice that this is a list of lists. When I flatten it, I have a list of 25 individual elements instead of a list of 5 elements, of 5 lists, each of them of 5 elements. And then we define those variables, 25 variables, each of them to have values between 1 and 5, right? Because each of them pertains to one of the houses, and there are 5 houses. We have always to restrict as much as possible, say what the domains are, try to be as precise as possible. And then in each group, the variables have to be different. Each person lives in a different house, right? So we have to say that the people are distinct, right? Because the name of the person, or the nationality of the person, will be assigned to a number which represents the house that it lives in, and each of them lives in a separate house. Also, each house has a separate color, a distinct color. So we say that all of them are distinct. There are 5 colors, notice, and 5 people, and then we have 5 houses from 1 to 5, so they will fit just nice. Same for drinks, same for pets, same for cars. And now we have the setup. We have set up the entire problem. So we can start encoding the comments, and look how nicely they work, right? So let me try to lift it a bit further so they are on the same level. All right, so the first constraint is the English woman lives in the red house. English equals red. That's all we have to write, fine? So English equals number means that the English person lives in the house with that number. Red equals number means the house with that number is red, and they have to be the same because that's what a constraint requires. The Spaniard owns the dog. Spaniard equals dog, right? Coffee is drunk in the green house. Coffee equals green. Oh, when I see that, I'm thinking like coffee is green. Yuck. Right. Coffee is drunk in the green house. The Ukrainian drinks tea. Ukraine equals tea. The green house is immediately to the right of the ivory house. Okay, so we're considering the houses from right to left, from left to right, and to the right means +1, right? So green equals ivory +1. BMW driver owns snails. What a weirdo, right? The owner of the yellow house drives a Toyota, right? And then milk is drunk in the middle house. The middle house is the third house. Milk is drunk. Norwegian lives in the first house on the left, so this would be the first house. Norwegian lives. No, the person who drives the Ford lives in the house next to the owner of the Fox. So Ford minus Fox in absolute value should be 1. That means neighboring. Is that clear? Same for Toyota driver and the house where the horse is kept, right? So Toyota minus horse in absolute value should be 1. The Honda owner drinks orange juice. The Japanese drives a Datsun. The Norwegian lives next to the blue house. So again, absolute value. And we're done, right? It's absolutely, the encoding is absolutely straightforward. It's, when you look at it, it screams at you that it's correct. All right? It's not that you have to think whether it's correct or not. It screams at you that it's correct. And then we do the labeling during combinations, and the answer pops up. Why am I emphasizing this? Because in general, in most software development, whenever we have large software development processes, right, teams of thousands of people developing software over a few years, developing in mainstream languages, maybe like C++ or Java, what happens is that you try to solve a problem and work on your code for 2 weeks, let's say, right? And then maybe 2 months later, or maybe a year later, you have to go back and add a new feature. So what happens is that you open the code that you have written, you yourself have written, and you might need to spend 2 weeks to understand what you have done a year ago. All right? So understanding code is not easy, and having the luxury of code that where you can understand what the code is doing, that doesn't happen very often, right? And it's a very good feature if you can have it. It will simplify the code development. It will help with code understanding and developing further features. It will reduce the time spent in debugging and testing, and so on. So this is an important feature to have. And for this particular kind of problems, right, this language is very, very expressive. It's very, very good at achieving exactly that. If you were to solve this problem in C or C++ or Java or Python, you would surely not write this number of lines, right? So you can essentially say that the code solving the problem is between line 33 and line 58, right? So it's about 25 lines, right? So surely you won't be able to write it in soluble space. Yeah. So that's one feature that one will have. Of course, you may say, well, how typical is this kind of problem? Well, what happens in general is that you can always define your own domain-specific language for any problem you have to solve. And instead of coding your problem into C++ or Java, you write a little interpreter for your domain-specific language, and then you solve those kinds of problems in that domain-specific language. It's a trend which people have started to take on more and more because it generally simplifies the process of software development. It reduces debugging and testing greatly. It performs a much better abstraction, right? The abstraction level is much better. All right, are we clear with the encoding of this problem? Is it clear? Let's run the code. I don't want to run the last part. Actually, I'm going to start from here. So Eclipse Prolog is a bit weird. It has a compile scratch path, but this one doesn't save, and something is wrong with it. It has a pure command line as well, which I actually prefer. So I can say compile all, code gets compiled, and then we can ask for a solution in main L, and we get one very, very fast, right? So you see the English woman is in the 3rd house, Spanish the 4th, Ukrainian in the 2nd, Norwegian in 1, Japanese in 5. Then the 3rd house is red, so the English woman lives in the red house. So on. 5th is green, 4th is ivory, 1st is yellow, 2nd is blue. Then in the 2nd house, tea is being drunk, 3rd house milk, 4th house orange, and so on. Okay? And we have individual values for every variable, so now we can associate with each house, house 1, all the 5 properties that pertain to it. Is this clear? We can try. I'm not sure what happens here. Same thing. So I have defined a predicate that takes advantage of some I think it's called print list. Yeah, so it sort of prints on separate. So prints a list of lists on separate lines. so we can see it better in this part right here. Okay, clear? Okay, last one. Seesaw. So this is in fact an optimization problem. So I have 3 kids, and they're on a seesaw. The seesaw has a number of seats, and they can sit in various places, and they would like to be as close to balance as possible, to the seesaw being fully balanced as possible. All right. So because the seats are placed in discrete places, and the weights are not necessarily I mean, they're essentially random. We cannot guarantee balance. We cannot guarantee that we always can create balance, but we can be as close as possible, right? So we can minimize over the set of all the solutions to obtain the one that is as balanced as possible. Now, what do we mean by balance? What's the measure of the level of balance here? When is the seesaw balanced? Level. Not like this or like this. Louder. Well, when the torque. Good, torque. What's another name for torque? Torque is at the wheel of the motorbike, right? Momentum, right? The momentum of the weight is as close to 0 as possible, right? So we're going to define as positive the momentum of the weight when it tries to rotate the seesaw clockwise, and negative anti-clockwise. So we're going to take advantage of that, so that all the momentums, what's the plural? Momentums, I think. All the momentums sum up to a value that is as close to 0 as possible. So we're going to try to minimize on that. So what's the momentum? It's the force times the arm times the sine of the angle between force and arm, right? If the angle is 90 degrees, then the sine is 1, so we can ignore the sine. And by weight, we mean mass times gravitational force times gravity, right? But because we're going to have an equation that we're trying to get to minimize it, we can actually simplify by gravity, which is a positive quantity, and just do the mass, which we typically refer to as weight, right? But it's not measured in newtons, it's measured in stone here, which can be converted into kilograms. Anyway, so we can do that and say weight times arm plus weight times arm plus weight times arm, and 1 to sum to 0. Whatever is on the left-hand side has to be negative, right? Now, there's another constraint. If we read carefully, there's another constraint here. They also wish to be able to swing their arms freely, requiring that they are at least 3 feet apart, right? So 3 feet apart. They have to be. So we have relatively simple constraints, just that we cannot be guaranteed to be 0. We could take the sum of the momentums and constrain it to 0, but then we may not get a solution. We're not certain to get a solution at that point, right? So we want to minimize it, and we're going to learn how to minimize it. And actually, it's extremely simple. So let's look at a code. And I'm going to, I should restart this guy. All right, so this is the solution, Ignore the rest. The rest is a generalization that is trying to compute a solution for many kids and many weights. So what are we saying? We're saying that this L is not good. Let's call it answer. So the answer is a list of 3 variables or 3 values, right, representing the positions of the 3 kids. LFS are the positions, right? And the position is in feet and has to be a whole number of feet because every seat is in a fixed place. We cannot place a person in between seats. Then all these variables have a domain between -5 and 5. So this is how we say domain in Eclipse instead of ins. Right, so everything is sort of similar but not quite the same. Then we have to say that each pair of kids, when we look at the positions have to be 3 feet apart. So we have to set the positions being 3 feet apart for all the pairs. There are 3 pairs, right? And then we define the momentum. So momentum is weight times length times arm, right? Weight times arm. Weight times arm, and we're expecting that one of these to be negative, or at least one of them. Some of them will be negative, some of them will be positive. And we call this the cost, and this is the amount that we want to minimize. Do we have to say that the variables should be distinct? Yes? Right, so that would be redundant, and in this case will not help. Right, the greater than 3, the distance between 2 kids being at least 3, already implies that the variables should be distinct. So adding all this thing would be redundant. And we've seen previously that redundant constraints help, but in this case they won't. So they would be a waste of typing. Not that much of a waste of time. You won't see that much difference in the running time, but you definitely would see a difference in the amount of typing you have to do. And see, normally if we were to impose this to be 0, we could just say that cost is equal to 0 and do a labeling. But instead of doing that, we use this predicate minimize, right, across all the combinations generated by this guy and looking for a minimum of the cost. And then we're going to print the solution. So how is this minimum computed? Naively, you may think that all the combinations are generated, then we just go and scan all the combinations and try to find the minimum, right? But that's not quite true. The process is in fact much more efficient, and it relies on the method called branch and bound, right, which is brought in by this library. So we're bringing in 2 libraries. The library for integer constraints, IC. It's actually interval constraints. That's what it's called. And interval constraints because, as we have seen also in SWI prologue, for variables, what we always try to keep track of is their limits, their bounds. Right? So that's an interval. So it's an interval constraint. And branch and bound is the method that can optimize in an efficient manner over arbitrary constraints. This is, pretty clever, as a matter of fact. All right, so let's run this first because it's just one predicate. Actually, we have to load this. So I just cleared it. Maybe we just restart. So some constraint solvers conflict with each other and they shouldn't be loaded simultaneously. All right, so we call main And oh, okay, it keeps making this error. So branch and bound requires reals. All these predicates that you see, all these relational operators, those who start with hash work on integers and impose integrality on its operand if it hasn't been imposed already. The ones that start with dollars require real numbers. You shouldn't think that hash is some sort of an operator that makes another operator work on integers or reals, right? It's a naming convention. So all the operators that work on integers have been named with a sequence of symbols that starts with hash. All the ones that work on reals have been named with a sequence of symbols that starts with dollar. So we're defining this to be unconstrained to integers. We don't want it to be integers. So we compile, and this one time it worked correctly. And now we call main A, and we get a solution, and we see the process of finding a solution right here, right? The program starts and first finds a solution with a cost of 57, right? This problem is underspecified. It has multiple solutions. If it weren't for the minimization, we could find many solutions that, because the only constraint is what? To fit between -5 and 5 and to be 3 feet apart, right? The complication comes from the fact that we want to minimize the cost, which is the momentum, right? So, but that's not it's just a minimization, right? So if we leave that aside, we only satisfy the constraints that were imposed, so being 3 feet apart, there will be many solutions. So the first one that is found is 57. Is a solution with a value of 57. And you see there 57 between two values because it's actually what they compute is an interval. And in general, the interval cannot be guaranteed to maybe be a singleton, right? But in this case, it just happens to be, especially because all values are integers. So what happens then? Normally, you would want to backtrack and attempt another solution, right? And it might be the case that you find a solution with a higher cost, one that is driving you away from your objective because you're trying to minimize. So as soon as you find a solution that has a higher cost, that's worse. So to prevent that and to be efficient, once the system has found this solution, it adds the constraint, it injects the constraint in the system that cost should be less than 57. The existence of such a constraint does what? Triggers a propagation process and shrinks the domains of all the variables, hopefully. We cannot guarantee that, but in general, we have seen that every time we add more information to the system, that information can propagate it and result in shrinking the bounds of the variables, and that reduces the search space quite dramatically, right? So what happens from now on, because the constraint has been injected, is that no solution with a cost larger than 57 will be ever found. Right? The search space has been reduced in such a way that no such solution exists anymore. If it existed, it has been shrunk out of the domains of all the variables where the constraint has been propagated. So the next solution that is found is one that has a cost of 53. And the process continues. As soon as this solution is found, it is reported, as you see, and a constraint of cost less than 53 is injected into the system. That results in more propagation, results in more shrinking of the domains. Okay? And the process continues slowly, and it so happens that in this case we actually do get a solution that has a value of 0, right? For which we have a printout of the values, right? But the fact that we have a solution of 0 is actually quite incidental. It's not. We don't have to have it, and it's very easy to produce something that a solution that doesn't have a minimum of 0. Let me just make this 35. Let's make the kids American. All right. So in this case, for instance, when one of the kids has a weight of, what do we say, like 35, the lowest cost is 1. You cannot find anything with a cost lower than 1. Right? And you see that there's no solution with cost 0. The system is figuring out that it should try to find a solution between 1 and 0 after finding the solution of 1.0, but it doesn't find any, so it concludes that the optimal cost is 1. Right? And you can play with the values as much as you like. So the larger the number here, obviously, the further away you're going to go from complete balance. Right, so now the minimal cost is 4, right? And you see the process, and you see that there's no solution between 0 and 3. So the system will try to find a solution between 0 and 3. We'll figure out that once it has found a solution with 4, the only thing that remains to be searched for is a solution between 0 and 3. If none is found there, then it can be concluded that the minimum is 4. Otherwise, the process continues. All right, so branch and bound is much more efficient than blind optimization that just scans through the space, the space of all the combinations, and just computes the minimum by the typical algorithm that you know. Right? Injecting the constraint based on the current local minimum reduces the search space further, even though you can't predict from the very beginning how much reduction there will be. There will be significant reduction in general in practice. Is this clear? All right. So again, we have a very neat language feature, right? It comes from this library, and all we have to do is, previously we would have just the labeling, now we have minimize over the labeling for a specific quantity, which is cost in this case. Is this clear? So you can apply this to much more complex problems. For instance, you can try to create a timetable for a school. Right? The school would have a number of classes, then a number of students, each of whom must take a set of classes, right? And a number of teachers who would teach. Each of them would teach some of the classes. Then there's a number of classrooms, and then there's a number of time slots. And the constraints are of the form that every student attends a single class at any one time, which is held in a single classroom by one teacher, right? No classroom contains more than one class at the same in one time slot. No teacher teaches more than one class at one time slot, right? And no student attends more than one class at one time slot. And then it's likely that once you have this, you would have multiple solutions for the timetabling problem, but you can introduce a cost, as for instance the level of unhappiness of students who have to attend classes in the morning, right? So for classes that start at 9 a.m., you make the level of unhappiness very high, and then at 10 you make it a bit smaller, and then you figure out a way to assign cost unhappiness levels to the classes that are available, and then you compute across the entire set of classes and students and teacher the overall level of unhappiness, and you try to minimize on that, right? Try to keep students as happy as they can be. Constraint optimization problem there. Okay. Okay, this is it. This is it for today. Any questions? No? See you next time. Or see you in class on Friday.